friends. Welcome back for our next segment in climate. Yesterday, if I recall correctly, we talked about factors affecting temperature and factors affecting precipitation. Well, we're going to be switching it up a little bit here today, and we're going to begin today with another major component of a driving force of climate on planet Earth. And it's an interesting word, or term, I should say, called the Coriolis Effect. So let's get down and dirty in our notes right now, and let's get started with describing what the Coriolis Effect is all about. Now, yesterday I showed you some diagrams, pictures of the major wind patterns on planet Earth found at different latitudes. And some of you might have been wondering, well, why do they go in different directions? Now that is a good question. Well, it all ties into this thing we call the Coriolis Effect. The Coriolis Effect can simply be described, whoops, I'm in the dark. It must have been nighttime there on the other side of the Earth. But we want to continue with our notes in the daytime, so let me just push the right button. The Coriolis Effect can be described simply as the shift in wind due to Earth's spin. It's really not quite as simple as that, but for our purposes right now, let's write that down. The Coriolis Effect is the shift in wind due to Earth's spin. And I want to try to describe some things to you. I may show you with a globe in class what actually is going on here, but let's look at this diagram. This is a good diagram, okay? The Earth, as you know, is a sphere. We don't live on a flat planet. It is a three-dimensional sphere. And as we know, it rotates on its axis. It rotates once on its axis every day. Now, I know in science we always use the metric system. So the diameter of the Earth is about 40,000 kilometers in diameter. But I want to use miles here for a moment because I think you'll catch on why. At the equator, in miles, it's about 24,000 miles. 24,000 miles is the circumference of the Earth. And it takes 24 hours for the Earth to rotate once on its axis. I want you to think about that for a moment. If you were standing on the equator like this little dude at location B, and you were on the equator in the course of one day, which is 24 hours, you would go all the way around the diameter, or rather the circumference of the Earth, which is 24,000 miles. So you'd be traveling 24,000 miles in 24 hours. Do you know how fast you would be going? Speed is equal to distance divided by time, and the distance is 24,000 miles. The time is 24 hours. You'd be going 1,000 miles an hour. Just by standing still at the equator, you're actually traveling at 1,000 miles an hour. Is that cool or what? Now, we don't live at the equator. We live up here at about 45 degrees north latitude. And where we are, well, if my math is correct, we're traveling at about 750 miles per hour, which is still pretty quick. It's almost the speed of sound, just standing still or sitting still where you are right now. We're going about 750 miles an hour due east. So if the Earth were to stop turning abruptly, we would all go flying off the planet in a straight line at about 750 miles an hour. That may sound pretty cool, but it would kill us. So we would not want that to happen. But don't worry, it's not going to happen. Now, why do I bring this all up? Here's why. The atmosphere of Earth is not physically attached to our planet. And so the Earth spins underneath the atmosphere. But there's a lot of drag, a lot of atmospheric drag. There's a lot of friction between the atmosphere and the Earth. And so as the Earth spins, it's also carrying with it the atmosphere, but the atmosphere doesn't all travel at the same time. Now, let's take this a step further. In the northern hemisphere, let's say you were standing on the equator and you wanted to travel north. Now, you could walk in a straight line from the equator to the North Pole, theoretically speaking, that is. And with a compass, you'd just travel in a straight line. But here's the deal. If you were in an airplane, if you were off the surface of the Earth and you tried to travel in a straight line, you actually wouldn't go in a straight line. You would be shifted in the atmosphere, because in the atmosphere, there is a shift to the right when traveling north in the northern hemisphere, because you're going a lot faster around the equator than you are as you get closer to the pole. Bottom line is this: if you tried to go in a straight line in the northern hemisphere, you would always be shifted to the right. That's what happens to the airflow or the wind in the northern hemisphere, because the Earth is spinning on its axis. That apparent shift we call the Coriolis effect. Now, in the southern hemisphere, it's actually the opposite direction. In the southern hemisphere, the shift is always to the left. And again, that has to do with the direction that the Earth is spinning. The Earth rotates on its axis from west to east. So that's why in the northern hemisphere, there's a shift to the right. In the southern hemisphere, there's a shift to the left. If we were on a different planet like Venus that rotates in the opposite direction, well, these directions would be different. But don't worry, we're not on Venus. We are on planet Earth. So again, the Coriolis effect basically states this. If you are in the northern hemisphere and the air is traveling somewhere, or you are traveling somewhere in the northern hemisphere, the Coriolis effect will always shift you to the right. If you're in the southern hemisphere, you will always be shifted to the left. I'll show you that diagram again. In the northern hemisphere, you're shifted to the right. Southern hemisphere, if you're going in this direction, you're shifted to the left, the actual path. All right. If you don't understand the dynamics behind that, don't worry too much. When we get to physical science and we get to motion, you'll probably understand a little bit better. What I need you to remember right now is this. If we're in the northern hemisphere, the shift is to the right. If you're in the southern hemisphere, the shift is to the left. That's what you need to remember. Now, let's try and put this into practice in our own state of New Jersey. Okay? So how might the Coriolis effect affect us here? Well, let's talk about it. Let's say that there is a high pressure system. And you remember from weather, from our last topic, what a high pressure system is all about. We've got the air coming down on top of us. And if this is the surface of the Earth and the air is coming straight down, when it hits the Earth with a high pressure area, when it hits the Earth, it's going to spread out. Think about pouring a glass of water on a table. If you pour a glass of water on a table, imagine the water is the air coming down. Imagine the table is the surface of the earth. What's going to happen to that water? It's going to spread out. Well, that's what happens on Earth with a high pressure air mass. The air comes down and then it spreads outward from the center. So as you're drawing these arrows, I want you to think three-dimensionally here. Imagine we're a bird in the sky looking down on our beautiful state of New Jersey here, and there is a high air pressure area. The air pressure is going to be coming down, hits the surface of the earth, and is spread out in all directions, not just north, south, east, and west, but in all directions like water spilling on a table. Now, hopefully you got that. Now, here in New Jersey, we are in the northern hemisphere. So because of the Coriolis effect in the northern hemisphere, which way is the shift going to be? To the left or to the right? To the right. So as this air mass moves out from the center, here's what happens. It is shifted to the right. So let's look at this top arrow first. The arrow is going northward, but because of the Coriolis effect, it's being shifted to the right. Now imagine you're standing on the H here and you're looking down this arrow, your movement is shifted to the right. Look in the other direction. Here's the arrow, shifted to the right. Looking south, shifted to the right. So all of the movement of the air is shifted to the right, and as a result, in the northern hemisphere, the airflow around a high pressure zone is going to produce a clockwise direction of airflow. Check it out. See the arrows? So high pressure, northern hemisphere, air flows out from the center, shifted to the right, and it produces a clockwise direction. Now, let's look at this picture here. This became a famous picture of a hurricane that devastated the Gulf Coast a number of years ago. This is a space view of Hurricane Katrina. It was a devastating hurricane, a storm in northern hemisphere, and it just did an incredible amount of damage to the Gulf Coast. But what I want you to look at here in this picture is the direction of airflow associated with a hurricane. Now, the very center is called the eye of a hurricane, and around that, you should be able to see a spiraling direction of airflow illustrated by the clouds that surround it. In fact, if you look at it, hurricanes in the northern hemisphere spiral in a counterclockwise direction. But let's find out why. Storms, like hurricanes, are associated with very, very low air pressure. Now, I want you to think about that example of water on a table. Pouring water on a table would illustrate the high pressure. Now, imagine that puddle of water once again on the table, but instead of pouring more water on it, we get a big old straw. Now, it would be disgusting if we sucked it up, so let's pretend it's a vacuum, okay? We put a vacuum hose in the middle of that puddle, and we suck it up. What's going to be the direction of the water flow on the table? Is it going to be flowing away from the vacuum or toward the vacuum? Of course, it's going to be toward the vacuum. That illustrates a low pressure area. A low pressure area in the atmosphere, indicated by the letter L, results in an inward flow of air. So these arrows are indicating that the air at the surface of the earth is flowing toward that low pressure area, the center of that low pressure area, and then is being sucked up higher into the atmosphere like a vacuum or a straw. Same idea, same idea. Now, the Gulf of Mexico, as you can see here, here's Mexico, here's the United States, Florida's over here. Same picture. We're in the northern hemisphere. So, what way is the shift in the northern hemisphere as a result of the Coriolis effect? Is it left or is it right? It's right. It's always right. No matter whether you're dealing with a low pressure or a high pressure, in the northern hemisphere, the Coriolis effect is always affecting the shift to the right. So as these arrows indicating airflow going toward the center from all directions, if it's shifted to the right, check it out. If you were a particle of air on this arrow going to the center, you'd be shifted to the right. If you were a particle of air on this arrow and you were going toward the center, you'd be shifted to the right. From this arrow, shifted to the right. From this arrow, shifted to the right. So what does that result in? It results in a counterclockwise direction of airflow. So from that original satellite image of Hurricane Katrina, knowing that this was in the northern hemisphere, you can see that it must be a low pressure area because the airflow is counterclockwise. Now, let's say you're approaching planet Earth and you know all about the Coriolis effect, but you are an alien coming to planet Earth and you don't know which way is north and which way is south. And you saw a storm that looked like this. Storms on planet Earth are always associated with low pressure areas, so you know this is a low pressure area. But which way are the clouds rotating? Counterclockwise or clockwise? Clockwise. So what hemisphere do you think this storm is in? The northern hemisphere or the southern hemisphere? The answer is the southern hemisphere. This is actually a similar storm like a hurricane, except in the southern hemisphere. They call it a cyclone. And this cyclone or hurricane-like storm is in the southern hemisphere, and you can tell from space because it is rotating in a clockwise direction. So there's an old question. If you flush the toilet in the northern hemisphere and you flush the toilet in the southern hemisphere, do they spin in opposite directions? The answer is, all things being equal, yeah, they spin in opposite directions. If you were to take a bath in the northern hemisphere, take a bath in the southern hemisphere, or fill up a sink and you let it drain, they will spin in opposite directions. I think I have a good video to show you in regards to that. Now, there are always other variables that come into effect. But if the body of water is large enough, and if the basin of the water does not influence things, they will rotate in opposite directions in the northern hemisphere as in the southern hemisphere. So all this talk about the Coriolis effect is interesting, but what does it have to do with the climate? Well, it has a lot to do with the global wind patterns. Forget about storms, which obviously happen all the time. The Coriolis effect also impacts the global wind patterns on planet Earth. So let's check this out, the global wind patterns, and add some arrows to our diagrams in our notes. Here's the deal. We saw yesterday a cross section of planet Earth and how we had those convection currents. We were looking at the side cross section. Well, because of those convection currents, only the bottom of those convection currents are hitting the surface of the Earth. And it's only the surface of the Earth that most of us come into contact with. Now, if you're an airplane or a hot air balloonist, that's another story. But here at the surface of the Earth, if you're a sailboat, for instance, you really need to be educated about the global wind patterns, which are affected by the Coriolis effect. If you draw these arrows in, you will see the following pattern. From 0 degrees to 30 degrees north latitude and south latitude for that matter, the winds are predominantly from the east to the west, but they are going not straight, but at an angle. They are shifted to the right. Or I should say toward the equator here. If you're in the northern hemisphere, they're shifted to the right. If you're traveling in the southern hemisphere toward the equator, they're shifted to the left. Hopefully you can see that. Just to pretend that you are on the arrow, facing the point of the arrow, and you can even rotate your book if you need to see how that works. So these latitudes here are called the easterlies, the trade winds, the easterly trade winds. In the mid-latitudes here, you'll see the arrows are going from west to east, both in the north and in the southern hemisphere. Again, the direction, the shift from the Coriolis effect is to the right in the northern hemisphere, to the left in the southern hemisphere. And this band of weather patterns are called the westerlies. And then finally, it reverses again in the polar regions. But once you got those arrows down, we're going to name on the side of your diagram, we're going to name those winds. It's the same three titles, both in the northern latitudes as in the southern latitudes, but there are three categories. The trade winds, otherwise known as the easterlies. We've got the westerlies and the polar easterlies. So we have these three major regions in the northern hemisphere, these three major regions in the southern hemisphere. And because of the Coriolis effect and because of the global wind patterns, there are also global currents that exist in the oceans. The oceans also exhibit a circular flow to them. We're not going to get into that in much detail other than to just state right now that that's what happens. In the northern hemisphere, the northern Atlantic Ocean rotates in a clockwise direction. In the southern hemisphere, it rotates in a counterclockwise direction. And that goes with the other oceans as well. So there's a lot going on here with fluid dynamics on planet Earth when it comes to the Coriolis effect. But let's pick this up a little bit more. The major climate zones. Because of the impact that the Coriolis effect has on wind patterns, and wind patterns affect precipitation, and the latitudes affect temperature, how does this all tie into the major climate zones? Well, towards the poles, we have the polar climate zones. In the mid-latitudes, we call them the temperate climate zones. And on either side of the equator, we have the tropical climate zones. And again, it's the same in the northern hemisphere as it is in the southern hemisphere. But what we're going to do right now is we're going to take a trip through these different climate zones and add some more detailed information about the temperature and precipitation in each. The polar climate zones are typically cold and dry. Cold, primarily because of latitude. Dry, primarily because of the pressure zone above them. So polar regions, cold and dry. If you put all of those pictures together, it kind of explains what's going on here. Temperate climate zones are mild and moist. That's the kind of climate zone we live in, generally speaking. mild, and moist. And that brings us to the tropical climate zone, which is hot and wet year round. Now, remember, climate is the weather over a long period of time. So, in the polar regions, it's cold and dry throughout the year, temperate, mild, and moist throughout the year. That doesn't mean we don't have fluctuations or changes in daily weather. We could have a sunny day. We could have a warm, hot day. We could have a cold day here in the temperate climate zone. There can be lots of fluctuation. But in the tropical zone, it's pretty much hot and wet year round. All right. Now, I've mentioned a few times about the temperate zone in particular and how there's more fluctuation in the temperate zone. It's because we experience here seasons of the year. Seasons are the annual changes in temperature zones. By the way, I love this picture here. If you look at this picture, this is really pretty. It goes from winter, spring, summer, fall, winter, spring, summer, fall, winter, spring, summer, fall. And it goes around and around again. Same is true here, winter, spring, summer, fall. Just some icons to illustrate the different seasons that we experience in the mid latitudes here in the temperate zone. But as we've said before, and we were talking about this last week with weather also, the seasons are primarily due to the tilt of the Earth. Because the Earth is tilted on its axis, when the northern hemisphere is tilted toward the sun, it's summertime in the northern hemisphere. But at the same time, the southern hemisphere is tilted away from the sun, it's wintertime. And at the other end of the year, the opposite end of the year, the opposite side of the year, the opposite side of our orbit, the seasons are reversed. But the seasons are caused by the tilt of the Earth. Now, we're going to finish up today by talking a little bit more about climate change. As you know, Earth has experienced a number of ice ages over the course of geologic history, and ice ages can be described as the cycle of temperature changes on Earth from warm to cold and back to warm again. Right now, we are certainly in an interglacial period because it is warm right now relative to the last ice age. And natural climate change, which includes ice ages, are due to changes in the Earth's orbit and in the sun's energy output. These are cyclical, which means they are predictable. They happen every so many years. And if you study the geologic history of the Earth, you know that we have experienced a number of ice ages and interglacial periods over the course of Earth's history. But right now, there's a lot of talk about climate change in the sense of global warming. Global warming can be described as a rising global temperature. And there is no doubt, no scientists disagree with the fact that the Earth's temperature is, in fact, warming. Nobody disputes that. And that global warming is due to greenhouse gases, both natural and human made. Now, the big debate, however, and we can talk about this a little bit more when this lesson is over. The big debate right now, and actually among scientists, it's not that big of a debate. It's more of a political debate than a scientific debate. But the debate nonetheless is, well, how much is the human contribution to climate change? And we can discuss this as a class in just a few moments. But I want to just emphasize the fact that there is no debate that the Earth is warming up. And if you live along a coastal region or in an area prone to flooding like Louisiana or Venice, Italy, and other places around the world, you know full well that the last few decades have resulted in a lot more flooding than in the past. But Tomorrow, I just want to end with this. Tomorrow, we are going to be doing a lab activity dealing with global climate patterns, and we'll get to that tomorrow. So for now, I'm just going to say bye bye.